Propnets are an alternative to GDL for expressing the dynamics of games. With a few additional provisions, it's possible to convert any GDL game description into a propositional net with the same dynamics. As an example of this, consider the simple game shown here. There's just one role, white. There's just one base proposition, and there are two actions. The two actions are always legal. The player gets 100 points if S is true, otherwise the player gets 0 points, and the game ends if Q ever becomes true. Notice the dynamics. If A is performed and S is true, then P becomes true. If P is false, Q becomes true. If Q is true, R becomes true, and if white performs B, then R becomes true as well. Now let's build a propnet for this game. We start with the game's physics. The base propositions in the propnet consist of the propositions defined in the base relation in the game description, namely S. The input propositions correspond to the actions defined by the input relation in the game description, namely A and B. We use the next relation to capture the dynamics of the game. Starting with the base and input propositions, we add links for each rule, using inverters for negations, AND gates for multiple conditions, and OR gates for multiple rules. In so doing, we augment the propnet with additional view propositions as necessary. The result is the propnet shown here, which is exactly the same as the one introduced in the previous segment. Okay, now we have more things to model to complete our game description. First of all, termination. We model termnet in the propnet by adding a special node for termination. In this case, terminal corresponds exactly to Q. Remember, the game is over if Q ever becomes true. So we could just use Q as our terminal node. However, for the sake of clarity, we can also add a new node, T, as shown here, and insert a connection from Q to T. Note that I've used a one-input AND gate. I could equally well have used a two-input AND gate with both inputs supplied by Q, but this is simpler, and the behavior is exactly the same. Rewards are handled analogously. We create a new node for each reward value, and we use the definitions for these values to extend the propnet further. In this case, goal of white being 100 corresponds exactly to S, so we don't really need to add a new node for that case. However, for clarity in our example, again, we have added a new node for this case and labeled it 100. And then we've also added a node for 0, which is true in exactly the other cases from the case where the goal is 100. Legality is by far the trickiest part for encoding GDL in propnets. There are various ways we can do this. The simplest method conceptually is to simply add one legality proposition for each possible action and extend the propnet to say that when these nodes are true. In this case, we would add two new propositions, LA and LB, for the legality of A and the legality of B. In this case, they're always true. The actions can always be performed. To model this, we add a self loop for each of these legality propositions, and we initialize that proposition to true. Because of the dynamics of transitions, the propositions will remain true indefinitely, meaning that those actions are always legal. And that's it. Once this is done, we have a propnet that reflects the game described in the given GDL. In the next section, we discuss how to use this propnet to play games.